Welcome to the deep dive. Today, we're embarking on a pretty fascinating quest, trying to understand the fundamental building blocks of our universe and the really ambitious theories that try to explain how it all fits together.
Exactly. The learner shared some really thought-provoking material with us, a couple of quite deep academic papers in theoretical physics, so that's what we'll be digging into.
We're looking at some truly profound ideas here in modern physics. It's kind of like trying to figure out the ultimate Lego set of the universe, isn't it?
That's a great analogy. What are the smallest pieces? And what are the rules for how they connect? How do they build everything we see from, well, tiny particles right up to the vast cosmos?
It sounds incredibly complex, and I'm sure it is.
Oh, it is. But our goal today is really to pull out the most crucial, the most, well, mind-blowing insights without getting too bogged down in the super dense technical stuff. We want you to come away with a sense of wonder, really, and maybe a clearer picture of this incredible intellectual journey.
That's the mission. We'll trace how our understanding has evolved. In high-energy physics, we'll kick off with the more solid ground, I suppose, quantum field theory, and the standard model that's our current best picture of the subatomic world.
Right. And then we'll venture into some more speculative territories. Attempts at grand unification, things like supergravity, string theory.
And perhaps most interestingly, we'll take a really good look at Heim's theory.
Hmm.
That offers a very unique perspective on all this, apparently.
It certainly does. We'll also touch on how these ideas might connect to the big picture, cosmology, the universe as a whole, and also their links to, well, the very strange world of quantum mechanics.
Okay, sounds like a plan.
Yeah.
Let's start by unpacking the foundation then, our current understanding.
So our best framework right now for the particles and the forces governing them is the Standard Model.
Yeah.
And the bedrock, the absolute foundation for that, is quantum field theory. Now, quantum field theory, it's built on some really elegant ideas about symmetry. Think about symmetry in a simple way, like a snowflake. Rotate it 60 degrees, it looks identical.
Right.
Well, these fundamental symmetries in physics are like rules saying the universe should behave the same way under certain changes, certain transformations. And when we apply these symmetry rules not just to objects, but to fundamental fields that permeate all of space, well, that's where the forces and particles we see actually come from. It's a really beautiful, powerful idea.
So it's like the universe has these deep down rules, and those rules basically dictate what kinds of particles and forces are even allowed to exist.
Precisely. These symmetry rules, they give rise to what we call gauge fields. And you can think of gauge fields as like the carriers of the fundamental forces.
That'd be the force carriers.
Yeah. So for electromagnetism, the gauge field is the photon, the particle of light. The Standard Model, it brilliantly pulls together several key pieces of this puzzle. First, there's quantum electrodynamics, QED.
Right, I've heard of that.
It perfectly describes how light and matter interact. How electrons and photons sort of talk to each other. Then there's the Weinberg-Salam model. Huge achievement. It showed that the electromagnetic force and the weak nuclear force, they're actually two sides of the same coin.
Ah, unification.
Exactly, unifying them into a single electroweak force. And then finally, you've got the quark model, which explains the strong nuclear force. That's what binds quarks together inside protons and neutrons, and also holds the nucleus of an atom together.
Okay, that does sound pretty comprehensive. It covers 3 of the 4 fundamental forces, right? Electromagnetism, weak and strong nuclear forces. But I know physicists aren't totally satisfied. What are the big gaps? What's missing from this picture?
That's a really critical question, because while the Standard Model is incredibly successful, it's passed a huge number of experimental tests with, well, flying colors. It's definitely not the final word. One of the biggest omissions, maybe the biggest, is gravity. The fourth fundamental force, the one we experience constantly, it remains stubbornly outside the Standard Model's framework. It doesn't fit in.
Why not? What's the problem?
Well, mathematically, trying to incorporate gravity as described by Einstein's general relativity into the quantum field theory framework leads to basically mathematical infinities that we can't get rid of. It just breaks down. Also, the Standard Model has quite a few parameters that seem, well, arbitrary.
Like what?
Like the masses of the fundamental particles, electrons, quarks, neutrinos. The model tells us what they are, but it doesn't explain why they have those specific masses. Physicists would much prefer a theory where those numbers just pop out naturally from the fundamental principles.
Instead of just having to measure them and plug them in.
Exactly. And there's more. The standard model doesn't really account for some huge cosmic mysteries, dark matter and dark energy, for instance. We know they make up something like 95% of the universe's energy density,
Right, the vast majority.
but they aren't part of the standard model's particle list. We see their gravitational effects, but we don't know what they are fundamentally. So yeah, these major limitations are the real driving force behind the search for something deeper, a more unified theory.
Okay, so the standard model, amazing as it is, leaves some pretty big questions unanswered. Gravity, particle masses, dark matter. So what were some of the first big attempts to go beyond it, to try and unify things?
Well, one really interesting path physicists explored involves something called supergravity theories. Now, the super bit here comes from an idea called supersymmetry, or SUEY.
Susie, why?
Supersymmetry proposes this really deep connection between the two basic kinds of particles: fermions, which make up matter like electrons and quarks,
And then our particles.
and bosons, the force carriers like photons and gluons. SUXY suggests that for every known particle, there's a superpartner particle of the other type.
So a matter particle has a force carrier partner, and vice versa.
Kind of, yeah. It's a very elegant symmetry mathematically. And supergravity theories tried to use this supersymmetry, along with principles of broken symmetry, to unite all four forces, including gravity, and describe all particles in one single structure.
Broken symmetry. You mentioned that. It sounds important, like things were more unified, more symmetrical in the past.
That's a great way to put it. The idea is at incredibly high energies, like in the very, very early universe, maybe fractions of a second after the Big Bang, all the forces might have been indistinguishable, governed by one larger symmetry.
Okay.
But as the universe cooled and expanded, this perfect symmetry sort of spontaneously broke. Like imagine a pencil balanced perfectly on its tip that's symmetric, but it's unstable. It falls over, breaking the symmetry.
I see.
So this breaking of symmetry in the early universe could have led to the distinct forces we see today at lower energies. Supergravity was an attempt to model this unification and breaking. But unfortunately, these theories ran into some pretty significant mathematical problems. Inconsistencies, difficulties with calculations. They ultimately didn't quite pan out as hoped.
So supergravity hit some roadblocks. What was the next big idea then? You mentioned superstring theory earlier. Did that grow out of these attempts?
Yes, exactly. To try and get around the issues with supergravity, physicists started exploring even more, well, radical ideas, and that led to superstring theory, often just called string theory. This involves a really fundamental shift in thinking.
How so?
Instead of thinking of elementary particles as zero-dimensional points like tiny dots, string theory proposes that the most fundamental constituents are actually tiny, one-dimensional vibrating strings.
Like microscopic guitar strings.
Kind of. And just like a guitar string can vibrate in different ways to produce different musical notes, the different vibrational modes of these fundamental strings correspond to the different particles we see: electrons, photons, quarks, everything.
Okay, that's a very different picture. But you also mentioned 10 dimensions.
Ah, yes. That's another key part of most string theories. To be mathematically consistent, these theories typically require more spatial dimensions than the three we experience. Often it's 10 dimensions in total, 9 spatial dimensions plus time.
Wow. So where are these extra 6 dimensions? Why don't we see them?
The idea is that they're compactified, curled up incredibly tightly at a scale far, far smaller than anything we can probe the Planck scale. Around 10 sub 35 sub meters, it's unimaginably small.
Like a garden hose looks like a line from far away, but up close it has thickness.
Precisely that kind of idea. These extra dimensions are thought to be curled up in very complex shapes, called Calabi-Yau manifolds, for example. And the specific way they're curled up, the geometry of this tiny hidden space, is what determines the properties of the particles and forces we see in our large, familiar dimensions.
Okay, that's pretty mind-bending.
It is. And superstring theory held enormous promise. It seemed to offer a way to create a consistent quantum theory of gravity and potentially unify everything. But it also has its own major challenges.
Such as?
Well, one big one is the sheer number of ways these extra dimensions could be compactified. There isn't just one unique way. There are maybe 10 sub 500 sub possibilities or even more. This leads to what's called the landscape problem.
10 to the 500, that's an astronomical number.
It's vast. And each different way of compactifying could lead to a different universe with different physical laws, different particles, different constants. It makes it incredibly hard to make specific testable predictions for our universe. Which specific vacuum of string theory describes our reality? We don't know.
So it sounds like this quest for unification, while producing these amazing creative theories, hasn't quite reached the destination yet. Which brings us to Heim's theory. Our sources really highlight this one as potentially significant, something deserving more attention. What makes it different?
Heim's theory, developed by the German physicist Burkhard Heim over many decades, really does take a fundamentally different path. It aligns with a growing idea in physics that maybe space itself isn't just a passive backdrop, but has much more physical reality, more properties than we usually assume.
So space isn't just an empty stage for particles to act.
Exactly. Instead of focusing primarily on particles and forces within space-time, Heim's theory proposes that the actual structure of space-time is deeply, fundamentally tangled up with matter and forces. The geometry is the physics, in a very deep sense. And what's compelling, as the sources note, is the amount of theoretical results from Heim's theory, like calculated particle masses that seem to line up remarkably well with experimental data.
That sounds promising.
It really does. It strongly suggests this is a concept that needs much more intensive study. It's complex, no doubt, and maybe not as widely known as string theory, but its potential successes are hard to ignore.
Okay, so Heim gives space a much more active role. What are the core ideas, the postulates of his theory? What's the foundation?
There are several really key ideas. First, Heim proposes the quantization of multidimensional space. So unlike the usual picture of smooth, continuous space, Heim suggests space itself is made of discrete, fundamental units of area.
Area, not length.
Area specifically, a fundamental area unit incredibly tiny based on the Planck length squared. The Planck length is about 10 sub 35 submeters, so we're talking unimaginably small pixels of area making up the fabric of reality.
Quantized space. That's a huge departure from the smooth space-time of Einstein's relativity.
It absolutely is. Second, Heim's theory introduces a novel cosmology, a picture of the universe's evolution, that leads to a specific kind of higher dimensional geometry. He talks about a Hermitian manifold geometry existing in a higher dimensional space, typically 6 dimensions, which he calls R6.
R6, okay.
Within this R6 space, the key mathematical object describing the geometry, the Hermitian fundamental tensor, isn't simple. It's described as being built up from more fundamental non-Hermitian tensors. It's a more layered, complex geometric foundation.
So more complex than the usual four-dimensional geometry of general relativity.
Yes, definitely. Thirdly, Heim aims for a complete geometrization of elementary particles. The idea is that at the micro level, the energy-momentum tensor, which describes energy and momentum distribution, is essentially proportional to a geometric quantity similar to Christoffel symbols, which describes space-time curvature. This proportionality leads to purely geometric eigenvalue equations. Eigenvalue equations often pop up in quantum mechanics, describing quantized energy levels. Here, Heim suggests the solutions, the eigenvalues, represent the fundamental properties of particles themselves, like their mass, derived purely from geometry.
Deriving particle properties directly from space-time geometry? That sounds incredibly ambitious.
It is. Fourthly, and this is really remarkable, Heim's theory claims you only need a very small set of fundamental constants as inputs. Just 4 non-derived empirical constants.
Only 4. Which ones?
The gravitational constant, gamma, the cosmological constant, lambda, related to cosmic expansion, the reduced Planck constant, Shaw, which governs quantum effects, and the speed of light,Cija. The theory aims to derive all other physical constants and properties from just these 4.
Wow. That would be revolutionary, reducing all those constants we usually just measure and plug in. What else is key to Heim's approach?
Fifth, particles aren't static points. Heim describes them as dynamic structures whose geometric properties change cyclically. They have an internal dynamics, like an oscillation.
An internal clock, almost.
In a sense, yes. Sixth, and this is incredibly compelling, the theory claims to derive the strict symmetry laws governing particles and theoretically determine their rest masses. This is huge. The standard model takes masses as inputs. Heim aims to calculate them from first principles.
Calculating the masses. That's the dream for many physicists. And the 7th postulate.
Finally, Heim posits a fundamental world equation. Think of it as a master equation for all of physics. The claim is that in one limit, making certain approximations, this equation becomes Einstein's equations for gravity.
Okay, gravity emerges.
And in another different limit with different approximations, the same world equation becomes Dirac's equations for relativistic quantum mechanics, describing electrons and photons.
So it bridges gravity and quantum mechanics, the 2 great pillars of modern physics that have been so hard to reconcile.
That's the claim. Essentially, it suggests that maybe, deep down, all physics is just the complex geometry of this higher dimensional space. Now, whether this incredibly ambitious vision holds up under further scrutiny and experimental test, that remains to be seen.
Absolutely.
But the sheer amount of theoretical data that seems to match observation, as highlighted in the sources, means it really demands serious investigation. It's a very different way of thinking about unification.
It certainly sounds like it. Now, shifting slightly, the source material also brings up some really fundamental challenges to how we even think about elementary particles. What contradictions or open questions do they highlight?
Well, one of the most basic contradictions is that almost all particles we currently call elementary actually decay. They break down into other particles.
That's right. If they're truly fundamental, indivisible, how can they fall apart?
Exactly. It seems paradoxical. And if you try to hypothesize that they are made of smaller things, you run into other problems. There's no clear analogy to binding energy like we see in atoms or nuclei. When particles decay, the energy released often seems too large compared to any plausible binding energy holding hypothetical subcomponents together.
That is a puzzle. It's like a single Lego brick spontaneously turning into smaller, different Lego bricks without any obvious glue holding them together in the first place.
It's a good analogy. And the sources point out, without direct experimental evidence of substructure, how do we really know if something is elementary or just a complex system we haven't broken down yet? We keep probing deeper with more energy, but maybe there's always another layer.
A turtles all the way down kind of problem.
Potentially.
Yeah.
And the source raises a really provocative idea related to quantum fluctuations, virtual particles constantly popping in and out of existence. If elementary particles have infinite virtual degrees of freedom, maybe quarks, the things we think make up protons and neutrons, aren't actually physical particles themselves.
Wait, quarks might not be real.
In this view, they could be non-physical quasi-particles. Extremely useful mathematical constructs for describing the strong force, yes. But maybe not fundamental entities like an electron seems to be, just convenient descriptions.
That's a radical thought. What's the alternative view?
Well, the alternative is supported by current experiments. Our most powerful particle colliders have found absolutely zero evidence of any internal structure inside electrons or quarks down to the smallest distances we can probe. This supports the idea that they are the fundamental, indivisible units.
So we had these two clashing pictures. Maybe quarks are just math, or maybe they really are fundamental points. It seems we don't definitively know yet.
We don't. It highlights how deep the questions go when we ask what elementary truly means.
Definitely. Now, the sources also mention some specific mathematical formalism and notation used in these theories. Can you give us a quick rundown, just so we recognize some terms if they pop up again?
Sure. The sources use macrohm and micromin terms from Tretter to distinguish the large-scale world from the quantum realm. For notation, it mostly follows standards, but with a few quirks relevant here.
Okay.
A letter with a hat over it, like X, means a matrix with a whole collection of its elements. If it's complex, X means the Hermitian conjugate that's taking the complex conjugate of each element and transposing the matrix.
Right, transpose flips it.
Exactly.
Yeah.
And instead of the usual AB for a commutator, A-ba, they use an older notation, AAA, which can mean either A-ba or A plus ba, the anti-commutator, depending on context.
Ah, so the symbol does double duty.
Yes. And for vector operators like divergence, gradient, curl, when working in more than 3 dimensions, like R6, they use a superscript n, like divin, grad, rotten, just indicating the dimensionality. And divin specifically means a scalar divergence, a particular operation, not the standard tensor divergence.
Got it. Little symbolic quirks for navigating these complex mathematical spaces. The sources also stress the crucial role of symmetry again, and the need for a theory that explains the particle mass spectrum.
Absolutely. Symmetry is fundamental. As we said, the standard model is built on it. But a huge goal is a deeper structure theory that explains why particles have the masses, they do the whole spectrum, and it needs to find the complete set of fundamental symmetries underlying all particle dynamics.
And the sources hint these might be different symmetries than the ones in the standard model.
Yes, it raises the fascinating possibility that the truly fundamental symmetries might be higher order symmetries, more abstract, operating at a deeper level than the gauge symmetries we currently use, like SU3, XU2, SU1 for the standard model.
Higher order symmetries.
It's like the symmetries we see now could just be shadows or broken remnants of a much larger, more profound symmetry governing reality at its core.
That's a pretty mind-bending thought. Okay, moving on. The source material then considers time and inertial mass, asking which is a better starting point for building a fundamental theory.
Right. The source points out something seemingly obvious. For anything to exist, it needs to persist for some non-zero time interval. Seems basic. But there's a subtlety. If you use that idea duration in time as your fundamental starting point, it kind of presupposes you already know something about the structure of space-time itself. Specifically, the space-time related to the fundamental units of matter, often called MQ in these texts. It's a bit circular.
You need space-time to define duration, but maybe space-time arises from something more fundamental.
Exactly. So the source proposes that maybe inertial mass, an object's resistance to acceleration of these fundamental MQ units might be a better, more logical starting point for deduction.
Inertial mass, EFMA, from school physics. How does starting there help understand something like gravity?
Well, starting from inertial mass, you can follow Einstein's logic leading to the principle of equivalence. That's the cornerstone of general relativity, stating that inertia and gravitation are fundamentally equivalent.
Right, the equivalence principle.
Yeah,
Like being in an accelerating rocket feels the same as gravity.
precisely. And a direct consequence is that every inertial mass must also be a source of a gravitational field. Now, if you consider each fundamental unit as an energy state, and you accept mass-energy equivalence, incandescent Sopico, then each MQ has inertial mass.
Yeah.
And by the equivalence principle, it follows logically that every single MQ must also generate a gravitational field, however incredibly weak it might be for just one particle.
So mass and gravity are intrinsically linked right down at the level of these fundamental units. The discussion then naturally goes to gravitational fields at this elementary particle level. What do the sources say about that?
They present a specific empirical relationship. Subisub is momentum, and subisub is a field vector representing acceleration derived from a potential subisub. This suggests a direct link between a particle's momentum and a gravitational field potential. But the source is careful to note this is just one piece. It also mentions the other well-verified predictions of general relativity on larger scales: light bending, gravitational redshift, signal delays like the Shapiro delay, the precession of Mercury's orbit.
The classic tests of GR. So the idea is the same principles apply down at the particle level.
Yes, that's the argument. The source posits that in the microme, there must be elementary gravitational fields associated with these MQ units. They're elementary because the MQ are seen as fundamental and gravity seems additive. The total field is the sum of the fields from all sources. The relation subisub LNGMQ describes a static field, so the source notes it needs generalizing for dynamic situations.
But what about quantum mechanics? Does gravity behave nicely like Einstein described down there? The uncertainty principle and all that.
The source briefly touches on that potential clash. Heisenberg's uncertainty principle limits how precisely you can know pairs of variables like position and momentum. The source speculates, perhaps somewhat controversially, that maybe in the deep microme, these variables might not be subject to the uncertainty principle in the standard way.
That's a big maybe.
It is. But regardless of that quantum puzzle, the core point emphasized is the necessity of these elementary gravitational fields linked to the fundamental MQ units.
Okay. The discussion then shifts to the interplay between the large-scale macrome background and these tiny microme processes, specifically regarding gravity.
Right. The source presents some equations for gravitational fields using symbols over A, G, and highlights approximations valid for very small source masses and low field densities, giving a glimpse of how gravity might behave in weak field limits.
Okay.
It also points out that temporal disturbances in the gravitational potential must exist. Think of tides caused by the moon's changing pole. These are disturbances in the space-time potential propagating at some speed. Let's call it subosub.
Like gravitational waves.
Exactly, that's what it hints at. But the source is cautious. While you might intuitively think subosub is just the speed of light c, it states that's still speculative and needs verification. It doesn't automatically assume they're the same speed at this point.
Interesting. Any other points about the nature of space-time here?
It mentions a parameter, right, in one of the equations. If future experiments showed Broch was negative, it would imply space-time might have a structure like Minkowski space, the flat space-time of special relativity, even within this more general framework. But that's just a possibility raised.
Okay, a lot of dense concepts there. The conversation then moves to how space-time structure and fundamental interactions might be deeply interwoven.
Yes, this is a really profound idea. The source emphasizes that space-time, as experienced by these fundamental MQ units, gets its metric character, how we measure distances and times, directly from the invariance properties, the symmetries of the fundamental interactions.
So the rules of interaction actually shape the geometry of space-time.
That's the core idea. Empirically, we know at least four interactions: gravity, EM, strong, weak, maybe more. These interactions have specific symmetries. The source suggests these symmetries define the metric.
Wow.
Then it looks at Einstein's field equation, where sub 12 g sub r equals old sub. It interprets the right side, the energy momentum tensor sub, as being proportional to a divergence-free structure tensor. The structure tensor acts as the source, exciting the Riemann geometry, the left side of the equation, which we perceive as gravity.
So gravity isn't just a force in spacetime. It is the curvature of spacetime, and that curvature is sourced by the fundamental structure related to interactions.
Precisely. And while Einstein's equation works beautifully in the macro, any deeper theory must reproduce it in the right limit.
Right, it has to connect back to what we know works. The discussion then drills down further to the idea of a microscopic metric and elementary structures at that level.
Here, the source introduces metric steps, denoted x sub quaternion. This strongly suggests a fundamental discreteness, a quantization of the metric itself at the smallest scales, maybe Planck-like scales.
Like spacetime isn't smooth but pixelated.
In a sense, yes. These metric steps are seen as equivalent to the energy masses of elementary structures, the MQ, which appear as tiny deformations of spacetime. Because spacetime is highly nonlinear at these scales, the theoretical masses, MQ, are expected to have discrete, specific values.
Which matches particle physics observations? Discrete masses, not a continuous smear.
Exactly. It matches high-energy physics data better than trying to apply standard quantum uncertainty to gravity, which often gives continuous ranges. This leads to the intriguing suggestion. Maybe the infamous difficulty in quantizing gravity comes from ignoring this fundamental discrete structure of spacetime itself.
So trying to quantize a fundamentally smooth spacetime might be the wrong approach if spacetime itself is discrete at the bottom.
That's the implication raised here. It's a very different perspective on the problem of quantum gravity.
It really is. The narrative then introduces world dimensions and a world tensorium. What's this framework about?
To handle this complexity discrete spacetime, interwoven interactions, the source posits a higher dimensional world called R6, 6 dimensions. Our familiar 4D spacetime, R4-3 space plus 1 time, is seen as just a subspace within this R6.
Okay, so 2 extra dimensions. Where are they?
They're denoted x sub 5 sub and x sub 6 sub, and they're considered normal or perpendicular to our R4. Together, these 6 coordinates C define this R6 world. A key question then is, are x sub 5 sub and x sub 6 sub real dimensions, or are they imaginary in a mathematical sense?
Does that matter?
Yes, because the signature of spacetime, how distances are calculated, usually plus bang, depends on it. Our R4 is plus bang. Depending on whether x sub 5 sub and x sub 6 sub are real or imaginary, there are 4 possible signatures for the full R6 world.
So we're stepping into a 6-dimensional arena, theoretically, to try and get a more complete picture. What are the implications?
Well, one implication is about an empty world. If there were absolutely no distinguishable structures in R6, the geometry would be flat, geodesic coordinate system C. But in the real world, with matter and energy, the metric tensor components become functions of all 6 coordinates. The relationships between different reference frames also depend on all 6 coordinates. It allows for much more complex space-time structures.
And our observed 4D physics comes from.
The idea is that the specific metric character of the MQ space-time structure we see in our 4D world is fundamentally shaped by the invariance properties, the symmetries, of the fundamental interactions occurring within this larger R6 world.
The discussion then introduces Hermitian world structures. What does Hermitian mean here? It sounds mathematical.
It is. Hermiticity is a specific type of mathematical symmetry, often important in quantum mechanics. The source states that due to a specific mathematical relation, called equation 6, not shown here, all the standard theorems of Riemannian geometry, the math behind general relativity, still apply to these R6 world structures.
Okay, so the mathematical toolkit still works.
Yes. Things like parallel transport, using Christoffel symbols derived from the metric tensor, work as usual. The time coordinate 10 is used as the parameter along geodesic paths in R6. This reflects that the structure's evolution over time can be anisotropic, different in different directions, across slices of this 6D space.
What does that imply physically?
It implies that motion components, x, are essentially accelerations determined by the Christoffel symbols, which come from derivatives of the metric tensor zubisub. So the components of zubisub themselves can be interpreted as universal tensorial interaction potentials.
Potentials that cause acceleration through interactions.
Exactly. This opens the door to a really radical idea. Maybe all observable physical quantities can be expressed purely as functions of the geometry, the connection coefficients related to Christoffel symbols, and the metric tensor, the Subi-sub, a complete geometrization of physics via these Hermitian world structures in R6.
Everything derived from geometry. That's
Yeah.
a powerful vision. The source then talks about energy density and hermitization.
Right. It mentions 36 discontinuous energy densities linked to the non-Hermitian aspects of our 4D spacetime, R4. These might relate to the different fundamental interaction components. These densities form an energy density tensor, Subic sub.
Okay.
Now, for a closed system, you can perform a mathematical process called hermitization, making certain quantities mathematically symmetric. But doing this requires that the divergence of this energy density tensored Subic sub must be 0 in the full 6D world, R6.
Like a conservation law in 6D.
Exactly. And crucially, this divergence-free property is preserved when you go from the microdescription to the macrodescription via the correspondence principle. The source also notes that a canonical energy density tensor in R6 must depend on the metric Subi-sub and its first and second derivatives. Analogous to GR, it suggests there's a unique divergence-free structure tensor in R6, derived from the metric and its derivatives under certain assumptions.
The source then introduces metronization. We touched on discreteness before. Is this related?
Yes, metronization is the core idea of making continuous quantities discrete, replacing smooth variables with fundamental, indivisible units, metrons. It's a very general form of quantization.
Okay.
The source presents equations, 7 and 8, involving a Hermitian operator H that seem to offer a path from the continuous infinitesimal description to this discrete metronized one. It states that if there are no discrete structural levels equal to 0, then the Riemann curvature tensor becomes 0.
Meaning flat space.
Yes, mathematically, it implies the pseudo-Euclidicity of an even higher 8-dimensional space, R8. And this flatness is identified as the criterion for a completely empty world. So the very existence of structure seems tied to this fundamental discreteness, this metronization.
So a non-discrete world would be an empty world. No stuff, no forces, no interesting geometry. The discussion also mentions microfluctuations and condenser flow.
It proposes that at this fundamental level, there might be transitions between real and virtual states of these structural levels, like tiny temporal oscillations. In stable situations, this could lead to a dynamic equilibrium of submicroscopic fluctuations.
Like a constant simmering at the bottom level of reality.
Kind of. And these fluctuations are suggested as the source of something called condenser flow, described elsewhere in Heim's work as a fundamental phenomenon of all material structures. It's also speculated these might be key to understanding things like electric charge later on.
Okay. Then electromagnetism and relativity get brought in. How do these fit into Heim's picture?
Well, the standard laws of electromagnetism relating electric fields, E, magnetic fields, H, charge density, Q, velocity, V, are the basis for the electromagnetic principle of relativity. The key idea there is that the E and H field components aren't separate. They combine into a single electromagnetic field tensor, F sub M sub, in our 4D spacetime R4.
Well, right. That's standard relativity.
Yes. And the source makes the point that photons, the particles of light, can be considered as imponderable MQ fundamental units with 0 rest mass. So even light fits into this MQ framework.
So massless fundamental units. The conversation then shifts to deriving gravity equations, starting simply with spherical symmetry.
Yes, assuming a simple case where gravity only depends on distance r from a central point, the math simplifies. The source relates the divergence of the gravitational field G to a function mu, which represents the mass distribution creating the field.
Okay.
By setting a standard for mu, like assuming identical density at some surface, and using the gravitational potential, it derives an equation linking div G to this mass function ember.
How does this lead to energy conservation in the gravitational field?
By integrating that equation in space and time, and then setting the total gravitational field energy, E sub sub, equal to the negative of the static potential energy of the source, E sub sub, it arrives at a key energy principle. M sub 2 sub plus 12 grat sub 2 sub TBV M sub 2 sub.
Yeah, so mass energy plus field energy, the integral term, equals the total source energy, M sub 2 sub.
Exactly. It shows the unity of the field and its source, representing the macro energy principle for gravity with some weak field approximations. Under spherical symmetry, this can be turned into a nonlinear differential equation for the potential Führer.
The discussion then looks at gravitational space structures and their extrema, maximum, or minimum points.
Right. It introduces transversal mass, M sub Q sub R 1 versus sub, for a moving mass, M sub. This form is important for relativistic invariance. Kinetic energy is also given in a relativistically correct form.
Okay.
For radial motion under gravity, free fall, the speed is v sub 2. The maximum possible value of this speed is linked to a reality extremum derived from an approximate solution. By applying conditions like submax sub and using approximations, the source derives simple relations for fundamental gravitational constants within this theory.
So fundamental constants might be determined by these extremum principles where things reach limits.
That seems to be the suggestion. It's tying the fundamental constants back to the structure and limits of the gravitational field itself.
Then the topic turns to the huge challenge, quantizing gravity. What's the perspective here?
Well, the source notes that while some equations, like 8 and 8a with the Hermitian operator, seem to hint at quantum gravity, they actually relate to microscopic structures involving general interaction potentials, not just gravity. It suggests gravity might be a non-quantum companion structure alongside other interactions governed by a different principle, principle C.
A non-quantum gravity. That's controversial.
Highly. And the source acknowledges there's currently zero direct empirical evidence for a quantum structure of gravity. But it argues, because of principle C and the existence of fundamental MQ units, there must be elementary gravitational fields associated with each MQ, even if they aren't quantized in the usual sense.
So the puzzle of quantum gravity remains wide open. The discussion then introduces corrections to the gravitational potential and revisits the energy principle.
Yes, a correction term is added to the potential FIRS involving the mass function MAR and a factor related to average atomic masses for Bose-Sub. The energy principle is then rewritten, separating known terms, E sub, from an unknown term, E sub A sub, which involves integrals of the G field and another field B. The density of this B field term, E sub, is likely related to how the mass m changes with radius r.
The fundamental constants come back into focus then, linked also to nuclear forces.
A specific equation, EQ12, is presented, relating several constants: gravitational constant O, a fundamental mass m sub, speed of light c, a potential sub, and Planck's constant h at a specific gravitational limit q.
Okay.
Approximations can be made. But determining the value of this limit q depends crucially on an assumption about the average masses Bose-Sub of the microscopic units making up the macroscopic source in Q. And the source states, making this assumption about Bose-Sub is basically equivalent to making an assumption about the nature of nuclear forces.
So it connects gravity to the nuclear realm through this parameter. The topic then shifts to cosmological redshift, why light from distant galaxies appears stretched.
Right. The source describes how a photon leaving a gravitational source loses energy fighting the potential. This energy loss means its wavelength increases redshift. It emphasizes that the entire mass distribution in front of the photon matters.
Okay.
While a full analysis is given here, it mentions a specific gravitational structure in 3D space, derived from equation 11, depending on the signs of potential fear G inside-outside radius Q. This is explored more in a dedicated cosmology chapter, analyzing Hubble redshift and radius. The conclusion here is that equation 11 has some explanatory power for redshift, but isn't yet a complete cosmological structure theory.
So this framework potentially explains redshift via gravity, not necessarily cosmic expansion, an alternative view.
Potentially, yes. It offers a different mechanism to consider. The discussion then looks at the limits or boundaries of these gravitational space structures. It presents conditions, 14a, b, c, defining different regions based on two radii, r sub and r sub plus sub. It notes r sub plus sub must be finite. Equation 12, relating constants, marks the location of inflection points of the solution, 11c, while conditions 14 give the physical reality limits of the solution under certain approximations. Together, these define the extrema of this gravitational structure.
The source then tackles distance and the idea of anti-gravitation.
It defines a distance measure E within a real compact 3D space, R3. Then it makes a strong claim. Anti-gravitation or repulsive force from negative or imaginary mass m sub cannot exist in this real R3.
So no anti-gravity in this model's basic space.
Not in R3, no. It does acknowledge the possibility of extreme mass densities in astrophysics, leaving black holes open. It also clarifies that a parameter t from another equation 15 shouldn't be seen as a world ether. The key next step, it says, is to synthesize equations, 8 and 15, into a unified description, which needs a formal math methodology for cases where TO0.
Okay. Then the concept of the metron reappears, along with metronic integration, back to the discrete picture.
Yes, the metron is the fundamental discrete unit. Metronic integration is defined as a limit of sums, analogous to standard Riemann integration. Standard integration is just the limit when the metron size goes to 0. A metronic differential quotient, like a derivative, is also defined for both continuous and discrete intervals using the metron unit.
How does this discreteness affect mathematical objects like tensors?
It leads to metronic structural tensors. The lower limit of summation now matters, affecting signs. Specific rules for metronic differentiation are given, and metronic integrability is defined. Can you find a function whose metronic differential day equals another function?
It seems even basic math operations need careful redefinition here. Multiplication, powers.
Absolutely. Metronic multiplication is introduced, and crucially, it's generally non-commutative. Order matters. AB might not equal BA. Metronic powers and roots are defined consistently. The source also discusses the dimension of the metron T and how coordinates themselves get metronized, involving an oriented coordination selector ZI, linking metron numbers to spatial orientation.
So directions and positions are quantized too. What about vector operations like grad, div, curl?
They're redefined too, using metronic differentiation. Metronic gradient, divergence, and rotation are introduced. And there are metronic integral theorems, discrete versions of Gauss's and Stokes' theorems from standard vector calculus, adapted for this metronized space.
This metronic space sounds fundamentally different from our usual smooth picture.
It is. Metronic tensors exist in a p plus one-dimensional Euclidean hypersurface embedded in a larger space. Introducing the parameter t as an extra dimension leads to general metric structures. Projection parameters sublink metronic coordinates to Neveu surfaces, surfaces of constant value. A condition FDO0 is argued to describe a general metric structuring arising from volume metronization. And importantly, the boundary of the metronic domain, highest metron number, must be invariant under coordinate changes.
The source then mentions even more complex metronic hyperstructures. What are those?
Okay, a simple tensorium is just a sequence of metrons. A metronic network structure carries the metronic fine structure of each p-dimensional subspace, Rp, within a larger n-dimensional space, Rn. A metronic hyperstructure in Rn is the most general form, characterized by three dimensionalities, m, n, and l, indicating its complexity.
And these have a fine structure selector.
Yes, the fine structure selector subsub helps define metronic fields of sum within these hyperstructures. There's also a combined functional selector incorporating L fine structure selectors. The source describes how the fine structures of simple tensoriums embedded in these hyperstructures are related through these selectors and metron numbers.
To make sense of this abstraction, they propose a metronic reference space.
Right. An n-dimensional space R sub O that's metrically empty is suggested as a good reference. Why? Because it has orthogonal coordinates and linear properties, making it mathematically simpler. Coordinates are linearly related to metron numbers via simple coordination selectors. This linearity makes it a good baseline for understanding the more complex hyperstructures. A metronic reference grid, x sub k sub, is defined using a linear grid selector, C sub E sub.
How does metronization affect the metric measuring distances in this reference space?
The coordinates in R sub O get fundamental orientations sub E sub. This allows defining an infinitesimal metric d sub. Transforming standard Cartesian coordinates leads to the usual metric tensor form d sub equals sup sub sup sub. Though Ribi sub might not be Hermitian here. The key step to the discrete tensorium is going from d sub to a discrete difference, a sub 2 sub, using the metron 0. This sub describes the geometry. From metronic differentiation laws, you can find n families of geodesic lines, straight as paths, defining the network of the metric structure. The volume element is also defined using the determinant of the metronic metric tensor.
Then there's a sieve operator. What does that do?
The sieve operator S acts on a general field function. It seems to be a way to relate the discrete metronic structure back to an underlying, possibly continuous field. When S acts on Talarno, some rows columns in a matrix representation degenerate into grid kernels, and their intersection defines a grid point in the metronic structure. A relation, U sub and sup po, connects the hyperstructure to the empty reference space R sub n sub. If the transformation matrix C is just the identity I sub, then the empty reference space itself becomes linearly metronized.
Even basic translations in vector fields get re-examined.
Yes, infinitesimal translations are metronized using a metronized structure function of sub. The change in a vector field due to translation appears as a change in the density of metron numbers in the projected empty reference space R sub n sub. Importantly, this density change is independent of the metric itself.
Then there's covariant metronization. How is that different?
It's a more sophisticated version that explicitly uses fundamental selectors. It handles both symmetric, Hermitian, and non-Hermitian cases. In the non-Hermitian case, connection coefficients are involved. Covariant metronization is possible under certain assumptions about these selectors. In the symmetric case, the connection coefficients are uniquely determined by the metric tensor components.
The source then introduces a condenser symbol and selectors. What are these tools for?
The condenser symbol involves the grid kernels we mentioned. It simplifies if the kernels are identical. A selector theorem relates various quantities. A functional selector is determined by a binary field kernel of a fundamental metric condenser.
These selectors sound quite general.
They can be. Tensor indices can become vectorial selectors with modalities E related to non-hermiticity. A very general condenser field selector with mixed variant multiplets is introduced, acting on metronic tensor fields. Selectors can also be built from different condensers with varying signatures. The source suggests metronic theorems might be developed for these, possibly involving the sieve operator. A composition field 2G is defined where fundamental condensers become J equals Ka0.
The existence of these grid kernels seems critical.
Yes, the source notes that proving the existence of exactly M3 grid kernels needs indirect proof. It also mentions that for dimensionality P2, the theory suggests 15 simple metronic tensoriums arise, forming 2D coordinate surfaces spanning a 12-dimensional space, R12.
The idea of a reference tensorium comes up again, specifically the tensorium of an empty world. Why is that preferred?
While any R6 hyperstructure could be a reference, the one for an empty world, R sub 6 sub O, is argued to be most physically suitable. It has linear grid selectors, making it the simplest reference structure. All metrons are identical, selectors are linear. Analyzing R sub 6 sub O avoids infinitesimal hypothetical partial structures. Metronizing infinitesimal structures relative to R sub 6 O focuses on relation 8. The source mentions the possibility of M3 tensorial grid kernel selectors, a hypermatrix, for partial structures arising from synthesizing equations 8 and 15, potentially confirming earlier heuristic ideas.
Interestingly, the source suggests a probability interpretation might be possible in some cases.
Yes, in a specific linear case, PLELT, a probability interpretation for the average state of all structural levels becomes possible. This is due to linear superposition of metronic eigenfunctions. The quantity supersup can relate to probability density. But importantly, this probabilistic interpretation doesn't hold for higher degree selector equations. It might be a special case.
Even core concepts from GR like curvature and divergence get metronized.
That's right. Metronizing the Riemann curvature tensor R supisup sub km sub gives a metronized version R supisup km sub n. Its trace yields the metronized Ricci tensor and scalar curvature. The tensor divergence in empty R6 becomes a condenser field selector. Vector divergence becomes supisup n. And the divergence-free infinitesimal structure tensor also gets metronized.
The concepts of a state selector and hermiticity keep reappearing.
Yes, the transition from infinitesimal to metronized form might require the state selector to be Hermitian in abstract function space. The trace in equation 8, related to energy with discrete spectra, is linked to a selector relation JKN AXTL, which synthesizes 8 and 15. This implies our real discrete point spectra, and K is a Hermitian state selector. Leading to the conclusion that metronic functions live in a Hilbert space, like in quantum mechanics. The discrete are interpreted as metrical structural levels or condensation levels due to TO, with the fundamental condenser defining the associated state function.
How do the algebraic properties and symmetries of R6 carry over to the microme?
The source states the algebraic properties of R6, Hermitian and non-Hermitian, are transferable to the microme, leading to specific relations, 3-3a. The symmetry properties should also reappear, determining the possible mathematical traces. A specific selector for the trace in IOP is given.
The source then introduces hermitry, the geometry of possible worlds. What's the core idea?
Hermitry is presented as an interpretive framework for understanding the geometries of possible worlds in k dimensions, f sub sub, guided by empirical physics. Anti-Hermitian coordinates exist outside f sub sub. A specific 3D subspace, r sub 3 sub, spanning 3 non-commuting imaginary coordinates, is seen as a key semantic architectural unit due to its compact properties.
What different forms can this hermitry take?
Under a specific condition, the possibility is reduced to just 4 classes symbolized H, X, Y, labeled A, B, C, D. They're classified by their condensation type, imaginary or complex, and coordinate hermiticity. A, R4 is Hermitian, B, R5 is Hermitian, C by 6 is anti-Hermitian, D, the whole R6 is Hermitian.
And these have physical interpretations.
Yes. A is primary self-condensation, B, time condensation, C, space condensation, D, space-time condensation. Forms without condensation levels relate to A. It's hypothesized these four forms might be elementary forms of matter, and transitions between them could represent a cosmogony, the origin of matter.
Then there's a world selector and a space condenser. What do?
The world selector L = KXX allows describing a key relation, EQ19, using the space condenser RAMM = XH. This selector relation has 1,296 component equations. Using the definition of the space condenser, it acts like a space compressor structuring space.
Anti-Hermitian coordinates and proportionalities also play a role.
Yes. Anti-Hermitian coordinates are defined based on the fundamental condenser's hermiticity. Hermitian symmetry relations, L or proportionality, are introduced. Two proportionality systems, J and MM, act as substituents, allowing simplification of general forms to involve only covariant condenser components, KML.
This leads to a solution and a spectrum of condensation levels.
A solution involving exponentiation and a linear selector H is presented. It includes a factor depending on metric steps, X sub KL, and the hermitry condition Q. This defines a new spectrum of condensation levels, X sub Xs O sub.
Approximations are then used to pick specific solutions.
Yes, the solution must extend to the infinitesimally approximated domain under certain conditions on X and a parameter A. An approximation is used to select a specific branch of the solution. New variables, U and V, are introduced, leading to a relation involving them and X.
The source then looks for extrema and relates them back to the fundamental Hermitian problem.
Right. Extrema of the behavior of U sub 2 sub are found by setting its derivative to 0. Substituting these back into the fundamental Hermitian problem yields conditions on the metric steps X.
And the source stresses the need for continuous correspondence between approximation levels.
Crucially, yes. All approximation levels must connect smoothly. The behavior of Hermitian components is determined by the linear selector H.
Different domains are then defined: metronic, mesome, infinitesimal.
Metronic is for low metron numbers, with specific approximations. Mesome is an intermediate domain with different approximations. Infinitesimal is the limit T-0, recovering continuous field functions with derived relations.
What about the macrome domain, our everyday world?
When a coordinate r is near a characteristic length q, an exponent becomes real, signaling a transition to the macrome. The correspondence principle applies. Quantum levels become dense, approximating a continuous spectrum. Individual elements, KL, are no longer distinct.
What about the anti-Hermitian transdomain?
The source argues against a continuous transition here for case A of hermitry, suggesting a discontinuity, G = constant 0. In case A, indices are only 5 or 6 covariant, and specific proportionality relations hold between condenser components.
Specific solutions are then given for the four hermitry forms, A, B, C, D.
Yes. Solutions for Y sub 2 sub for forms A and B involve functions F with specific forms given. Constants C sub 1 sub, C sub 2 sub. Form A is linked to R4 coordinates under conditions like a geodesic null line. For form C, a transformation simplifies the infinitesimal structure field equation, leading to a relation for phi. The equation reduces further with variables P, L, N, P, Q, L, N, and R, yielding solutions for P and R involving integration constants.
A time law and an equation for the R5 structure are derived.
Yes, a time law for I involves constants F, K, parameter O must be constant. This leads to a differential equation for the R5 structure variable W.
What about the separation constant and anti-Hermitian domains?
Conditions on the separation constant R arise from the behavior of W. The constant C can be imaginary or real. If C is imaginary, the 2D anti-Hermitian space R2 cannot be the spacetime of form. This implies the anti-Hermitian domain can only be the 3D space R3.
Then gravitons and condensation come into play.
In R3, only gravity exists. With propagation speed super sub equals C, a null line process is interpreted. If form A world lines are geodesic null lines, in R4 represents a gravitational disturbance propagating at C. Since the A spectrum is discrete, these disturbances should have discrete quantum levels gravitons.
Ah, a potential origin for gravitons.
Yes, the ambiguity in parameter F is resolved to below 0. Condensations not mapping to anti-Hermitian subspaces must intersect R5. A time-separated differential equation for an R4 function P is given. Div grad P equals O sub P2 plus P sub 2 sub, where OE relates to eigenvalue components from equation 19.
The source then discusses real R3 grids appearing alongside imaginary ones.
Yes, for selector bout in form B, real R3 grids appear. Also for high metron numbers, second validity domain, a quantity E sub becomes -1 for forms C and D, allowing approximation to the third domain.
Focusing on form C, what about its eigenvalues?
For real, even eigenvalues, a cosine term is +1, so only imaginary eigenvalues and odd real ones count here. A singular surface G sub 2 sub 2 sub plus R sub 2 sub is excluded, dividing the condensation domain into R sub 2 sub G sub 2 sub and R sub 2 sub J sub 2 sub.
This leads to specific spectra and a key relation.
25. Yes, eigenvalue spectra for form C are given. Then relation 25, R area U 2 sub 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 plus 1, 2 sub sub plus 1, involving integers n sub sub n sub sub. This must hold for all forms, AD. It implies n sub sub n sub sub if RD. Since R is 0, real distance, this connects R3 to other units via two integer systems for RGRG is a decaying near field.
So critical distances R in R3 arise from complex condensations defined by quantum numbers.
Exactly. And in this approximation, x sub a sub e sub equals 0.
What about neutral corpuscles?
For them, only K sub c matters for the eigenvalue spectrum. Equation 25 is used with specific quantum numbers to describe eigenvalue behavior for Rg. With n sub sub, n sub sub, the singularity at R remains.
The dove hermiticity and a force density selector are introduced.
A relation for F hermiticity is given. For Dau fields, a partial structure, index Q, can be used, still satisfying 19 and 19b, but with Dau. This leads to a non-zero R3 force density selector X as X0.
Focusing on space-time condensation, what about the R4 components?
The A space field is characteristic here, so only R4 components matter. Relations for these as X0 are given, involving volume element dq and proportionality factors for energetic E and structural F parts of the E field.
What about masses of imaginary condensations and elementary charge?
Relation 26 gives masses m and n of imaginary condensations. Relation 27b gives the elementary charge field involving radius r sub sub. Speculatively, the factor 3 in the charge relation might hint at composition from 3 partial charges. 27c.
A world metron is introduced with cosmological consequences.
Yes, the world metron from 15. The cosmogonic relation 37 from Vol 2 links the largest distance d in physical R3 universe diameter free of other constants. Differentiating d with respect to world time leads to a quadratic equation for a quantity w. Druscher showed this has 3 solutions for w.
Leading to a cosmological sphere trinitet. A trinity.
Yes. Setting initial conditions, W1 sub J sub, Q1A gives 3 solutions, sub containing D implicitly in quadratic equations, positive negative branches. For N1, NICWQ has 1 solution. The 3 temporal steps of updating this trinitet sub justify relation, 53.
The source then discusses the cosmogony of matter itself.
It defines a time interval for matter's origin. Certain symmetry groups hold them. Symmetry breaking at θ sub j suggests initial formation of neutral maximons, Planck mass, hypothetical particles with the maximum possible mass allowed by quantum gravity. Their decay into Messenberian cascades is proposed, metaphorically like cosmic inflation. An environment sub day is defined, and the behavior of the metronic line element near sub is discussed.
Abstract set theory is used to investigate R0's structure and cosmological motion.
Yes, for the R initial state, for N1 T0, only 1 solution D exists, linked to show. Another length D exists, linked to show in R6. For N3, a first development stage is complete with DD show changing with NTC. Relations involve DD and constants of Page. A threefold updating of the sphere trinitet at the beginning is suggested. DN and DN development from T0 to T is described.
What about symmetry groups during this cosmogony?
Permutation of dimensions N, M happens only within their own spaces. Symmetry group G applies during the first step, H for T sub 0 sub. The overall group is H, GXH, XGXH, isomorphic to another involving direct products of symmetric groups.
Elementary lengths in cosmology are connected.
A relation between D00 linked to elementary length sub J sub 6 sub, expressed via psi sub Q sub and dole. These metronic lengths exist since the cosmogony.
A tensor scheme in R12 and energy densities are mentioned.
48 components can form a rank 8 tensor scheme in R12. Elementary lengths relate to energy densities, suggesting energetic links. R4 equals R8 and R8 equals R12. Expressions for ep sub j sub ep sub 6 sub involve sex q sub dole and a dimensionless factor.
Wavelengths and energy generation are linked.
Psi sub sub and all dole, psi sub q sub are interpreted as wavelengths, giving m sub sub psi sub sub of constant. The transition psi sub co sub bol due to m sub sub is linked to energy matter generation proposed to occur at t sub. Dimensionality of the energetic subspace in R12.
It depends on the number of elements eliminated from set L. A sum is interpreted as a vector of length A, forming a volume element A in R4.
Timeless coordinates and scale factors.
Ordinal coordinates not energetically conditioned, beyond organizational ones, are timeless. Elements from relation E relate to scale factors pivot sub.
Length differences and projection are discussed. Assuming dole is a multiple of sub-sub, condition F1 holds for Ft, length differences, sub J sub, sub go sub are sums involving dole sub sub, sub sub sub. Limits bow are discussed, relating to results from Vol 2 involving R3 projection and organizational coordinates x sub x sub 6 sub.
Element creation annihilation linked to metronic condensations.
Its suggested elementary lengths are create annihilated in an R8 volume element. This corresponds to creating annihilating metronic elements in R4, changing metronic condensations according